Hi, everybody. This is Dr. Nigro with the Chem Calculation Screencast. This screencast is not really about calculations, I have to admit. It is focused on how to determine what intermolecular forces may be present and then how those intermolecular forces can impact physical properties of elements and compounds or mixtures of elements and compounds. So, no calculations here, but information that is useful and very important when thinking about reactions and solutions and just how matter interacts with other matter. All right, so as a reminder, the important part of the word intermolecular forces is that ER. All right, that intermolecular force occurs between or among, depending on what you're thinking, um, molecules or elements. These are forces of attraction. All right. So they're dictated by Coulomb's law, just like anything else. All right. They are, however, weaker than our other forces, the intramolecular forces. Those intramolecular forces are the forces between atoms within a molecule. We actually often refer to them as our chemical bonds. All right, but those are forces of attraction. The word bond is very easy to use, but in reality, it's not like a straight line appears between the two nuclei of an atom, right? It's the overlap of their orbital clouds, and two electrons get shared between those two atoms. But the sharing occurs, and the strength of that attraction is due to Coulomb's law, the charge themselves, and then in particular, the distance between those charges. All right. So when we talk about the different forces, there are a lot of forces in terms of intermolecular forces that we can have depending on what types of compounds we are dealing with. All right. So that means understanding what ionic compounds are is important, and being able to determine a polar molecule versus a nonpolar molecule is going to be very important for determining what intermolecular forces are possible and which ones are present. So if you need help with either of those two areas, please make sure you go back and look at those screencasts before continuing on, because I don't want you to get confused. Okay. Now, you'll note in here this table of intermolecular forces that I have. I've got a list of forces, a picture that shows you what they are, and then what's causing that force in specifics, and then the strength of those forces. This last column right here is the strength. All right, so we'll start with the first one. It's an ion dipole force. All right, so it's the force that occurs between an ion with a charge and a dipole's charge. So you're going to need an ion and some sort of polar molecule for this particular force. The ion is providing the ion charge, the dipole charge is because you have a polar molecule. All right, that's pretty straightforward. One of the strongest intermolecular forces that you can have. All right, it's the reason why things like sodium chloride are soluble in something like water. So we have ions form in a polar solvent. All right, up next, hydrogen bonding. So hydrogen bonding is a polar bond to a hydrogen dipole charge. So that means it's a polar interaction between a molecule's dipole, one end of the molecule, and a hydrogen or an oxygen, nitrogen, or fluorine that is attached to that hydrogen. So for hydrogen bonding to be possible, you have to have the hydrogen attached to one of these very electronegative elements, nitrogen, oxygen, or fluorine. If you have a CH bond or a pH bond or a BRH bond, none of those are considered hydrogen bonding, because those elements outside of hydrogen are not excessively electronegative, such as what we see for oxygen, nitrogen, and fluorine. All right, but you can see that is a very strong intermolecular force compared to the rest of the list. So that's going to be your strongest non-ion intermolecular force. All right, up next, we have dipole-dipole. So dipole-dipole interactions occur when you have polar, sorry, let me Switch back to my pencil. When you have polar molecules, but do not have hydrogen bonding capabilities. All right, so you can see that we've got a decrease in strength, but still pretty strong for an intermolecular force. But again, you have to have polar molecules. All right, that dipole is due to the unequal sharing of electrons throughout that molecule, and we get a buildup of poles, a positive end and a negative end to those molecules, which then allow them to line up positive to negative between molecules. All right, up next, we have our first induced intermolecular force. So I want to pause for just a moment to talk about that word induced. All right, induced in general just means caused. All right, so it's causing something. All right, induced interactions in intermolecular forces basically means a molecule that is not normally polar is induced to become polar because of what is it interacting with. All right, and the strength of these induced, whoops, that's not how you spell that, of these induced forces depend on the whoops, of the electron cloud around an atom, if it's a lone atom, or molecule. All right, so polarizability is going to be a very important idea when you compare molecules that are similar, but they are nonpolar. So, which of these molecules is more polarizable? All right, the easier it is to polarize one of these molecules, the stronger its intermolecular forces are going to be. All right, so basically when you talk about the strength of one of these intermolecular forces, it's going to be inversely correlated to the force of attraction, all right, between those electrons and its own nuclei. All right, but generally speaking, the larger the electron cloud, the more polarizable the atom or molecule. All right, and what that really means is more mass equals larger electron cloud. All right. So when you're comparing two atoms, for example, all right, let's say we're looking at two of our noble gases, argon versus xenon. All right, xenon has a higher molar mass, which means it has more protons, which means it in turn also has more electrons. All right, so that increase in the electron cloud makes it more polarizable, right? Those electrons are further away from the nucleus, so the force of attraction is a little bit less, which means that they can be pulled to one side of the molecule or another by an outside force compared to something that's much smaller, say neon or even helium. All right, so more mass equals a larger electron cloud, which means more polarizable. All right, so just keep that in mind when you're comparing compounds, as we'll see when we talk about physical properties. That's where the comparison comes in. All right, but let's go back to our ion induced dipole. All right, so for an ion induced dipole, what that means is you have an ion and you have some sort of non-polar molecule. And when that ion gets close to that non-polar molecule, if it's a positive ion, it's going to cause the negative charge in that density, that cloud around your molecule, to shift towards that positive ion because of the attraction. All right, if it's a negatively charged ion, all right, then the electrons are going to move away from that negative charge. So you get a induced dipole, a buildup of positive space versus negative space. But if the ion's not there, then the molecule is nonpolar with no poles. So there's no induction of that dipole. You have to have the ion present. All right. As you can see, the strength of those is less than a dipole-dipole interaction, around 3 to 15. All right. Up next is an dipole induced dipole. All right. So that means you have a polar molecule and a non-polar molecule. All right. So you have some sort of polar molecule such as water. right? It has a permanent dipole, right? It's polar, right? So there's a positive side to the molecule and a negative side. And when that molecule comes close to a non-polar molecule, the positive end of that polar molecule induces the electrons in that non-polar molecule to move towards it. So you get a buildup of charge across your non-polar molecule, an induction of a dipole. All right. So you can see this strength is less than what we saw with ion induced. There is some overlap. All right, and that overlap is due to the variation in strength of the polarizability of these nonpolar molecules. If you have something that's highly polarizable, you're going to get a stronger induced dipole for those guys. All right. And then finally, dispersion, also known as London dispersion forces. All right. This is a nonpolar interaction. All right. So if you think about it, electrons are moving, and at any one time, maybe one of your nonpolar molecules in your sample, the electrons just all happen to be on one side. So you get a temporary dipole that forms in that particular nonpolar molecule. If that temporary dipole then induces a dipole in another molecule, then your next nonpolar molecule now has an induced dipole, and then it just moves throughout your sample, these inductions of dipoles due to this initial temporary dipole. As you can imagine, that is a pretty weak interaction. However, similar to what we see for our ion-induced dipoles and dipole-induced dipoles, there is a range, and you can see the upper range is pretty high. So these London dispersion forces can actually be relatively strong if you have molecules that are highly polarizable. All right. So if you have something with a large electron cloud and it can be polarized, then you're going to get a stronger intermolecular force that builds there. Okay, so again, you need to recognize these 6 different options for intermolecular forces, and you need to be able to look at the molecules that you have and decide which one is present. All right, so that is what this next table is for. All right, this is the flow chart that I use. All right, it's how to determine which IMFs are present in a sample. All right, again, what I said above holds true. You must know if molecules are ionic, whoops, are ionic, or if they're polar, or if they are non-polar. All right, which means you need to recognize ionic versus covalent. All right, if it's covalent, that means Lewis structures. And you need to be able to calculate the bond polarities by using the difference in electronegativity and determine whether the molecule is polar or nonpolar. Again, I have a whole screencast on bond polarity and molecular polarity. Make sure that you look at that because you need that information to be able to use this flowchart. Okay? All right. In addition, for your information, as the atomic mass for elements or molar mass for molecules increases, so does their polarizability. All right, that is most important for our nonpolar molecules. Okay. All right, so let's look at this chart. All right, so the first thing I always ask myself, are there ions present? So is my compound ionic or is it covalent? All right, if there are ions present, all right, then you look and see, well, do I have the same substance? So in other words, do I have a pure substance, just a molecule, or do I have a mixture? All right. If I have a mixture, then I have to ask myself, are polar molecules present in that mixture or not? If the answer is no, if it's just ions, then you just have ionic bonding. It's not really an intermolecular force, it's an intramolecular force. So this is intramolecular molecular force, all right, which is a very, very strong interaction. If instead you have a mixture of ions and polar molecules, then you are going to have your ion dipole forces. All right. So, examples, like I said, any ionic compound dissolved in water is an excellent example of ion dipole forces. You've got the ions interacting with the polar ends of your polar molecule. All right. Now, on the other side are the other options, right? No ions are present. Although I should say that there's one that's not here. Let's see. Oops. Let's go this way. Non-polar. So if the answer is, are there non-polar? Well, maybe I should do it this way. Yes. All right. Then you have an ion-induced dipole. Now, this does not happen all that often because we're going to learn that things that are similar in terms of intermolecular forces play together a lot better than things that are different. All right, so nonpolar molecules and ionic compounds don't really play very well together. All right, but if they did, you would get an ion induced dipole intermolecular force. All right, so now let's move on to the other side. No ions. All right, so that gets rid of ion bonding and ion dipole and ion induced dipole. That's all gone. All right, so next up, what about polar molecules? Are there polar molecules present? If the answer is yes, right, then you need to look at those polar molecules and see, do you have any OH, NH, or FH bonds? If you have any of those bonds present, right, then you have hydrogen bonding as your strongest intermolecular force. All right, so ammonia is a great example of a compound that utilizes hydrogen bonding. Water, any of our alcohols, they all utilize hydrogen bonding. All right. If the answer is no, so we don't have any hydrogen attached to those elements, all right, then what we've got are dipole forces, all right? And this is assuming, all right, that we have pure substances, all right? Or we have a mixture of polar and polar, all right? If you have a mixture of polar and non-polar, that's where you get your dipole induced dipole forces. All right. But that's not on this script. All right. And then finally, what if you don't have any polar molecules? So everything's non-polar. All right. So then that means you're going to have London dispersion forces only. All right. So our choices are London dispersion forces, dipole induced dipoles, dipole dipole forces, stronger dipole dipole forces, hydrogen bonding. And then we can have ion induced dipoles, ion dipole forces, and then finally ionic bonding. All right. The strength is increasing from the weakest nonpolar interactions up to the ionic interactions. Okay. So you need to be able to look at what you have in your sample and decide what types of intermolecular forces are being utilized. Now, we are always going to focus on the strongest. That doesn't mean it's the only one, but it is going to be the one that influences the physical properties. Okay, so we have the below pairs of molecules. If they were mixed, list all the non-covalent interactions that would be involved. And we're not going to do all right? Instead, we're going to do the strongest because it gets complicated. All right, so NH3 and NH3, these are both polar molecules, and we have NH bonds. All right, so that means the strongest intermolecular force we're going to see with a sample of ammonia is hydrogen bonding. All right, which is a strong dipole-dipole interaction. All right, up next, we got magnesium ions dissolved in water. So we've got an ion and we have a dipole, I mean, it's not a dipole, a polar molecule. So this is going to be ion dipole interactions. All right. In addition, depending on the amount of magnesium, there's also going to be hydrogen bonding, but it's going to be a little weaker than our ion dipole interaction. But if we have just water molecules interacting with each other, we're going to get some hydrogen bonding. All right. Cl2 mixed with H2. All right. So these are both nonpolar molecules. All right, so this is going to be your London dispersion forces. All right, I also tend to call these LDFs. Okay, these are going to be very weak intermolecular forces. All right, SO2 and H2S. Now, somewhere you need to do the Lewis structure of these guys, and you need to look at them and decide whether they are polar or nonpolar. All right, should you do that, you will find that SO2 is polar, as is H2S. Now, neither of these has hydrogen bonding capabilities. Remember, the hydrogen needs to be attached to a nitrogen, oxygen, or fluorine. Sulfur doesn't count. All right, so these are going to be dipole dipole interactions. So the dipoles of these two molecules are going to line up so that the positive ends interact with the negative ends and vice versa. All right, then finally we have acetic acid and water. All right, so acetic acid, whoops, is going to be polar, as is the water. All right, but both have hydrogen bonding capabilities. All right, so we're going to see hydrogen bonding here. All right, so that's what you need to do to determine what type of intermolecular force is present for these particular molecules. All right, now I realize this screencast is long, but this topic is complicated and takes a little bit of time. So we're just going to do it all in one versus split it up. So next we're going to talk about the impact of the strength of these intermolecular forces on the physical properties of our pure substances and our mixtures. All right, there are several physical properties of atoms and molecules that are influenced by these IMFs. All right, we're going to go through each one of these. There are a couple others. I might mention them, but I'm not going to get too deep into them because we don't see them that often. But we'll talk through a couple of them. The first one is well, I'm going to start with the state of matter at room temperature. All right. Now, obviously, if you adjust the temperature, you can adjust the state of matter. All right. But generally speaking, strong IMFs, these are it's going to stand in for intermolecular force, favor condensed states of matter. All right, so something that has really strong intermolecular forces, say an ion-ion interaction, likes to be a solid at room temperature, which is why sodium chloride is a solid at room temperature versus a liquid versus a gas. So strong IMFs are going to favor those condensed states of matter, whereas weak IMFs favor non-condensed states of matter. All right. So a great example would be octane. It's a component of gas. All right. At room temperature, octane, which is a nonpolar molecule, utilizes London dispersion forces, which are very weak, prefers to be a gas. All right. That's because the force of attraction between the particles is weak. Therefore, they don't group together as much as you would see for something like NaCl. All right. So the state of matter is one physical property that can be influenced by the strength of your intermolecular forces. All right, next, volatility. Now, volatility is right on there with the state of matter. All right, it's a measure of a substance's tendency to vaporize at a specific temperature and pressure. All right, as the strength of the IMFs increases, so as that strength increases, we already said molecules favor condensed states of matter, which means they don't like to be a gas. Their volatility decreases. All right. So substances with strong intermolecular forces tend not to form gases. They tend not to vaporize. All right. If you've ever sprayed cologne or if you've ever sprayed perfume or deodorant, anything with a scent, right? That scent is made up of some sort of molecule that has weak intermolecular forces. So it vaporizes as soon as it is out of the can. It is no longer under pressure. So it vaporizes. Right. So it has high volatility. All right, so as the strengths of the IMFs go up, their volatility is going to go down. They'll be less likely to form a vapor. All right, up next, vapor pressure. All right, now vapor pressure is always a tough physical property for students to grasp. All right, it's basically the pressure exerted by the portion of a liquid, usually, it could be solid, but it's rare. The pressure exerted by the portion of a liquid sample that is in the gas phase. All right, now I think this is a little easier if I show you a picture. All right, so let's say this is a liquid. Let's just say it's H2O. All right, at any given temperature, there is going to be a portion of that liquid H2O, those particles that have enough energy to escape the liquid phase. So you're going to have some particles of water that are in the gas phase. All right. These particles will then move around, and every now and then they're going to bump into the surface of the liquid phase. And when that happens, that is pressure, specifically vapor pressure. All right. So any liquid is going to have a small portion of gas that hits the surface, that exerts the pressure. That's your vapor pressure. All right. So the question then is, how does the intermolecular force influence this vapor pressure? All right, well, let's think about it. As the strength of the IMFs increases, the amount of gas, oops, one S, particles decreases. All right, so that makes sense. As the strength of the intermolecular force goes up, everything comes more condensed. You have less particles that are able to overcome that force of attraction and escape into the gas phase. All right. If you have less gas particles, then you have less vapor. And if you have less vapor, you will have less vapor pressure. All right. So as the strength goes up, the vapor pressure goes down. So a substance that utilizes London dispersion forces as its strongest intermolecular force is going to have more vapor present because it has weaker intermolecular forces, which means more particles could hit the surface, which means a higher vapor pressure. And vice versa for something that has a really strong intermolecular force. All right. Now, the next physical property is right in line with vapor pressure. It's called boiling point. Right, I represent it all the time with BPT. All right, and boiling point is the temperature, which is the energy that is needed for the vapor pressure to equal the atmospheric pressure. All right. Now, that seems a little strange, but if you think about boiling, so think about a pot of water. All right. Initially, nothing really happens, right? It's heating up. The particles are utilizing that energy to start moving faster and faster and faster. Eventually, though, you see bubbles form on the bottom of your pot, but they don't rise. They just sit on the bottom. So that's a small portion of your water molecules that have converted into gas, but they don't have enough pressure inside of that bubble to push it up through the water against the atmospheric pressure that's pressing down on the water. Eventually, however, they gain enough energy that the vapor pressure inside those bubbles is at least equal to the atmospheric pressure, which allows them to rise and then pop at the surface. All right. So the energy that's needed to put in to your sample to allow that to happen is the boiling point. So when you add in enough energy so that the bubbles can rise, you have boiling. And so that is your boiling point. All right. Now, how does this relate to the IMFs? All right. Well, let's think about it. Stronger IMFs means lower vapor pressure. Wait, here. All right. So that means you don't have much gas present yet. All right. So you're going to need a lot of energy to get that vapor pressure up to equal the atmospheric pressure. So stronger IMFs means lower base vapor pressure. So more energy needed to equal the atmospheric pressure. And that more energy means a higher boiling point. All right. So a substance that has very strong intermolecular forces, it's going to take a lot of energy to get those particles to vaporize enough so that you have enough pressure to counteract the pressure of the atmosphere pressing down on your liquid. So strong IMFs mean high boiling points. If you have something with weak IMFs, it already has a high vapor pressure because of those weak interactions, which means you don't need that much more energy to equal the atmospheric pressure. So you're going to have a lower boiling point for those particular substances. All right. The last two we don't come into contact with too much, but we're going to define them just so you can know what they are. The first, viscosity. All right. A viscosity is basically its internal friction of a moving liquid. It's basically ability to flow. All right. So some substances flow really well, right? You pour them out, they pour all over the place, they make a huge mess. Other substances, they flow slowly. All right. Great examples of something that flows slowly: syrup, corn syrup, maple syrup, any of those are going to flow very slowly. So we say they have a high viscosity, they are resistant to flow. All right. When it comes to intermolecular forces, stronger IMFs equals more viscosity. All right. So something, let's say, uh, let's go back to ethanol. All right. Or not ethanol, sorry, octane. All right. Octane, nonpolar molecule, London dispersion forces, weak intermolecular attractions. That is going to have a very, very low viscosity. That stuff wants to flow. All right. If you have something else like a glucose solution, all right, it's got a lot of hydrogen bonding capabilities on that molecule. All right, you're going to get a very viscous, syrupy, slow flowing, high viscosity sample. All right. So as the strength of the IMFs increase, those molecules want to stay together. They don't want to just flow all over the place. They want to stay where they are. All right. And then last, surface tension. All right, surface tension is weird. It's an elastic force that acts upon the surface of a liquid. All right, it's basically what allows water bugs to scoot across the top of water versus falling into water. It's what causes water when it is in small amounts to form balls instead of just a big flat mess. All right, so surface tension, it's a force of those top surface particles on the particles below themselves. All right. If we were in physics, we could get way into that, but we're not, so we're not going to. But we are going to appreciate that stronger IMFs equals higher surface, oops, tension. Okay. All right. So these are the 6 different physical properties that are most influenced by intermolecular forces. There are others, there are many others, osmosis, all that kind of stuff. But these are the ones we're going to talk about. And in particular, we focus on vapor pressure and boiling point. All right. So at the very least, you need to understand those two. I would then back that up with volatility and state of matter. I think those 4 kind of all go together, whereas viscosity and surface tension are kind of one-offs. All right, so for these molecules, which of each pair would you expect to have the higher boiling point? All right, so before I even look, I know that strong IMFs equals high boiling point. So that means within each pair, I'm going to identify which of that pair utilizes stronger IMFs, and that is going to be the substance with the higher boiling point. All right, so I've got HCl, which is polar, versus Br2, which is nonpolar. So that's going to mean HCl with its stronger IMFs is going to have the higher boiling point. All right, CH3F is going to be polar. CH3OH has hydrogen bonding capabilities. All right, so that hydrogen bonding is going to take that CH3OH above CH3F in terms of intermolecular force. All right, HCl, polar, NaCl is ionic. So that NaCl's ionic bonding is going to be much stronger than HCl's polar interactions. So we're going to have a higher boiling point for NaCl. H2O utilizes hydrogen bonding. C2H6 is a non-polar molecule. How do I know that, you ask? Because because carbon doesn't like to have lone pairs on it, likes to form 4 bonds, and hydrogen will put a bond on each side, and the CH bond by itself is nonpolar. So most carbon hydrogen compounds with nothing else in there will be nonpolar. All right, but H2O is still going to win. All right, I2 and N2. Now, both of these are nonpolar. So then it comes down to polarizability. Which one is more polarizable? That's the one with more mass. This one, I2, has more mass. So it will be the stronger intermolecular force. Now, those are weak dispersion forces, but still. All right, next, which of each pair would you expect to have the higher vapor pressure? All right, well, I know that that strong IMFs equals low vapor pressure. All right, because remember, the stronger the IMFs, the more condensed the state tends to be, the less vapor we're going to have. So we're going to have less vapor, which means less vapor pressure. So I'm going to be looking for the weaker of these pairs for the higher vapor pressure. All right, so SiO2 is non-polar, SO2 is polar, so it's going to be my non-polar SiO2. And again, you might ask, how did I know that SiO2 was non-polar? Well, I could do the Lewis structure and I could see that it's nonpolar, or I could remember that silicon and carbon are in the same group. CO2 is nonpolar, so SiO2 is also nonpolar. All right, up next, CH4, which is going to use nonpolar NH3 hydrogen bonding capabilities. So that's going to be CH4 as the weaker and therefore higher vapor pressure. Argon and xenon, both of these will be nonpolar. All right, and it's going to come down to mass. All right, so the more mass is going to be with xenon, which means it's more polarizable, which means a stronger intermolecular force. So argon gas will have the higher vapor pressure. CCl4 is nonpolar, CH3NH2. So this NH2 group has hydrogen bonding capabilities. So the CCl4, the carbon tetrachloride, will be the weaker IMFs, so the higher vapor pressure. And then CO2 is non-polar. CH2O is going to be polar. How do I know? Well, I know it's going to look something like this. All right, where there's going to be a polar bond right here. So that molecule is polar, whereas CO2 is not. All right, again, this is where if you need to go back and refresh yourself on drawing Lewis structures, not a bad idea. All right. All right, so those are the types of questions that you're going to run into, comparing things, explaining why one has a higher this versus that. And it all comes down to these IMFs. All right, so remember those intermolecular forces are due to the interaction between the particles, not within the particles, but in between them. So you could have ions interacting with ions for very strong ionic bonding interactions, an ion interacting with a polar molecule to give you ion dipole interactions. All right, within polar interactions, maybe you have an HF, an HN, or an HO bond giving you hydrogen bonding capabilities. If not, maybe it's just dipole between two polar molecules. Or if you have an ion in the presence of a nonpolar molecule, maybe it's an ion induced dipole. Or if you have a polar molecule in the presence of a nonpolar molecule, maybe it's a dipole induced dipole. Or finally, temporary dipoles inducing other dipoles with nonpolar molecules and nonpolar molecules, giving us London dispersion forces. Okay, so again, you need to understand what we mean by intermolecular forces. You need to be able to identify what particular force is present, and then how the strengths of those forces are impacting the physical properties of your pure substances or your mixtures. Okay?